Hey everyone, so this lesson is based on the adversarial robustness, and this is based on the tutorial of 2018 by Mir IPS. This lesson is on the chapter 1, and we'll talk about the notations of the adversarial machine learning, and in general first we'll talk about the notations used in the in machine learning. Okay, so first is the model. So how do we represent the model? So model can be represented as an h theta, and this is, we can call this as a mapping from an input space to an r-dimensional, k-dimensional set of real numbers. So this h theta is a model that is to be trained. You can write it as model to be trained. And why are we writing theta? Theta represents the field, our parameters. So theta represents parameter, and this x is, we can call this as a 3D tensor, and this gives us the k-dimensional logit vector. So if this mapping is we have used for the ImageNet, then k will be 1000 classes. If it's a binary, then it may be 1 or 2 classes. So we can call this as a logit vector. And we are calling this as logit vector because these are not the probabilities. So we just pass this to one image to this model, which is as theta, and it gives us k-dimensional real vectors. Okay, and when we're training, so initially this k-dimensional real and this logit vector will not match our output. For example, we can say that our highly predicted class may be the 1, but it is predicting something maybe 0th or maybe 10th class. So initially it may not match, but we train this model so that it matches with our output. The highest value in the logit vector should match with the index of the actual true class. So that's the objective. And for that, we use the loss function. And the loss function can also be defined as a mapping. So this loss function and take this, the logit vector k, and maps it with the true class, which may be 1, 2, 3, maybe 1000. So we're taking it as a z positive, positive integer. So we're not starting with the index with 0, maybe just from the mathematics point of view. So our index starts from the 1. So this is z. So based on these two values, the logit vector as well as the true index, it gives us a real number, a positive real number. So this is a loss. So the objective is that this loss should be less if the logit vector is correct. Means the logit vector will be correct when the highest value will be for the true class, and if it is not, then this loss should be high. So that's the objective. And this loss that we are using is the cross entropy loss. So we can say that basically we can write loss is a function of h theta of x. So we have this, we are given this x as an input to the h theta, and this is the, you can say this is the predicted output, and we give the y, which is the actual output, and this gives us something called a real number. And this is the loss, which is, we are calling it as cross entropy loss. We'll have a different video that the integrity about the entropy loss, but for the time being, we'll just assume that this is a cross entropy loss. Okay. So now what happens in the training? So before that, what happens in the training, we need to know what is the training data set. So the training data set can be represented as a set of xi and yi. So what does it mean is that xi belongs to the input set, 3D tensors, and what is yi? Yi is the true class. True class means this one, z plus. So yi will belong to some positive integer. So this is our training set, and this I varies from 1 to m. So when we say m, means there are m training examples. So there are m training examples. And what is the optimization? What we want to do here during the training. Optimizing means that we want to first compute the total loss. So what is the total loss when we have run all the examples of the training sums? We have m examples, so it means that we'll compute loss for one example, then we'll compute for loss for second example, and then we'll add all of those examples. So let's say that the loss for one particular example is, we know this notation, this is L of h theta of x and y. This is the loss for the one particular example. And if we want to compute for all the example, then we can say L h theta of xi and yi. And then we need to add all of this loss. So we can write I is equal to 1 to m. M are the total training example. And this is our total loss. And if we want to find out what is the mean loss or average loss, we can call this as an average loss is nothing but 1 divided by m of the total loss. So we can, because there are m examples, so that's what we can do. And next is what we want to minimize. So what we want is that theta should be selected such that this total loss or the average loss is minimized. Okay, so we can say that our optimization problem is we want to minimize and we want to choose theta such that this average loss, which is 1 by m sigma L of h theta of xi with yi, I varies from 1 to m. So we want to minimize this loss. Okay, and in order to minimize this loss, it's a very difficult thing that we can do like this one, that we load all the examples inside the, and then we compute the two average loss together, and then we use the back propagation method to change the theta parameters of the model, which is the theta. So instead of what would be, the reason is that computers may not have that memory to load all of, to run all of these examples in one go. So what we use is we use mini batch stochastic gradient descent. So we use mini batch instead of computing the loss over all the examples, which is 1 by m of this one. So we just want to find what is the loss for one batch only. Okay, and then we continuously we keep on updating the parameters, and then we move to the next batch, and then we move to the next batch. So this is what we do. So in the mini batch, what we'll do is compute. So this is the important step. So we compute gradient and of loss. So we are computing the gradient of loss with respect to theta. So this is very important step because these steps will change when we will create an adversarial example. So we are computing the gradient of loss with respect to theta. And why are we doing that? Because we want to modify the theta and with respect to the loss. So our objective is that loss should reduce. So and whatever we want to modify, so we want to find out the gradient with respect to that only. Okay. So, and how do we modify? We modify a small adjustment to theta. So, because that's why we find out gradient with respect to theta, so that we can modify the theta. Or modify theta, or maybe we can just say adjustment to the theta to the negative direction of the gradients, so that this next time it will be reduced. So we update the model parameters towards the negative direction of the gradients. Okay, and then what will happen is we need to find out what is first batch, because we want to do that. Okay, so let's say our batch is now will be a subset of examples from 1 to m. We have xi yi up to xm ym, so let's say this is our mini batch. So let's now compute the what is the gradient of loss with respect to for this particular batch only. Okay, so far the loss will be again loss of L of h theta of x, but what is the gradient of the loss? So we want to compute this one, gradient of loss with respect to theta. So our loss is equal to L h theta of x. This is y. So this is the loss function, and then the gradient of loss can be represented as, because we're doing this gradient with respect to the theta, so we can write it as del theta. This is the gradient of loss and of the h theta of x and y, and this is the gradient of loss. Now what is the gradient of loss for the mini batch? And similarly, gradient of loss for the mini batch. So if there are maybe 32 examples, we have created a batch. So then this is the gradient of loss, the total loss. So, and then we need to divide it with the for the mini batch addition, and then we need to add all of these, and then we need to divide with the mini batch. So let's say there's there are we can just use the norm, that we have a norm of B, and then we can do the sigma of all the losses. So we can say gradient of, take this one, gradient of loss of h theta xi and yi. So this is loss, and then I varies from 1 to, now I doesn't vary from m. I is not from to m. So better is that we can just write that I belongs to the mini batch. So we have defined that mini batch is a subset of m. So we can just say that this gradient of loss for the mini batch is summation over all the examples which are part of the mini batch. Okay, so we got the gradient now, and now what we do is, what is the adjustment that we need to do in the theta? Adjustment in theta is based on generally with the learning rate, because we don't want to do the complete adjustment whatever is there, otherwise this will be very oscillating thing. So we want to take a small step at a time. So what we'll do is, let's say the learning rate is alpha, so then theta will be adjusted like theta. So we want to update towards the negative direction of the gradient, and this is the gradient of loss. So what we'll do is, we'll multiply this with the minus alpha, and we'll add this minus alpha to this one, or we can say multiply with the alpha negative of this one. So this will be like, is equal to, theta is equal to theta minus alpha by the size of the batch size, we can say, and then total loss, I mean the total gradient of L h theta of xi, yi, and I belongs to the batch. So this is all about the adjustment, and we repeat this step until the parameters converge. Repeat this step until parameters converge. So what is the repetition? So we have considered like one batch, and then we'll consider for the second batch and third batch. Once we have finished all the batches, then also we'll start this process again. So finishing all of the batches is called, that when we have finished all batches, we call that we have done one epoch. And once we had done one epoch, then we go to the second epoch and third epoch and fourth epoch until the parameters converge. So how do we know that parameters has converged? So we will see that loss has been reduced. So it is not getting increased, and it is not getting reduced also further. So we will say that these parameters have been converged. Okay. So now what we're going to do is, we are going to create the adversarial examples. Now, how do we create an adversarial examples? So the magic of the logic that we have into adversarial example is the again the computation of the gradients. So far what we have done is gradient of loss. So what we have done so far is gradient of loss with respect to theta is, this is del theta loss of h theta of x y. This is what we have done so far. So it computes that how to make small adjustment in theta. So what is the objective here? How to make small adjustments in theta so that loss is reduced. And we know that if we compute the gradient and we add negative direction gradients into the theta, and then this loss will be reduced, because loss is also a parameter of h theta of x. So next time when we'll again compute the gradient, so it will be less than what it had previously. So this is what we know that, and we can compute using the back propagation. So I'm not covering the back propagation here. Now, in what we'll do is adversarial. So the adversarial objective of the adversarial is how can the loss be increased. So the adversarial wants to increase the loss. Okay, and adversarial has no control over the theta. The model is always at the server end. So we already have this h theta, so we can't do much in that. So it cannot change the model parameters such that then instead of minus alpha, it adds plus alpha. So that is not something possible. But what is in the model's control, adversarial control, is the x. X is an input to the model. So h theta is cannot be, but x can be changed. So question is, can x be changed? And if x can be changed, then how can we change the x? Okay. So the idea behind this one is, so far we have done gradient of loss with respect to theta, because our objective was change the theta. So now if x has to be changed, then our objective is gradient of loss. So loss can easily be computed. So gradient of loss with respect to xi. Now instead of theta, it is xi. Okay, and make small changes in xi. Again, make small changes. We're writing small because these should not be visible to the human eyes, and we have seen the coding examples that it's not visible. So make small changes in xi to increase the loss. So it's better to watch the official videos also to see more exact case of in the useful or use cases for the adversarial machine learning. Okay, so that is the job of the adversarial. So what adversarial is going to do? So adversarial ways, we have still L of h theta of x y. This is the loss, and what adversarial is going to do is it will add some delta here, L h theta of x plus delta y, and it is going to maximize this one. That how can I maximize with delta, and this is over the capital delta, and this capital delta represent the set of perturbations. Delta is set of perturbations. So what we have is, this is a set of perturbations, and the adversary want to find out one perturbation so that if this delta is added into S, this is maximized. Okay, and if this one, if the adversarial want to maximize this one, so what is to be minimized? Negative of this function, because we are always using the neural network to minimize, not to maximize. So this optimization problem can be converted to minimization problem like this one. Minimize delta over the set of all the perturbations minus loss. So you just put minus, and this is h theta of x plus delta and y. So this is the minimize. Okay, and a common perturbation set to use is that what we want is that this delta should not be visible to the human eyes. So our objective is that this should be less than some number. Okay, and that number should be very small. Okay, and in order to define that, that should be very small, so we can write like this one: this delta is equal to a set of delta where such that norm of this delta, infinity norm, is less than equal to epsilon. So infinity norm means any number of this delta set should not be greater than epsilon. So we know that L infinity norm is a vector. L infinity norm is L infinity norm is of a vector is defined as z infinity is equal to actually maximum of zi magnitude. Okay, so whatever is the maximum element, if that is less than epsilon, and epsilon we have controlled, it means this set of perturbation is not highly that it should be visible to the human eyes. Okay, so once this problem is solved, so once this xi has been and this delta has been found, and then when we add this x plus delta, and we have seen that the model gives the wrong output. And this can be created, this same concept can be used for the targeted attack. So targeted attack means that at one point of time we want to increase the loss. So we are going to increase the loss with respect to true class. Okay, and at the same time also reduce the loss with respect to target class. So maybe that true class is 5. So the objective is that with 5, the loss should increase, but we want this class, this image to be predicted as class 50. So what at the same time, we also want with respect to class 50, this loss should be reduced. So that's the targeted attack. Okay, so what is the optimization problem here? So we can write that our original problem was that we want to maximize and we want to find out delta from the set of perturbations such that this loss of h theta of x plus delta y is maximized. And this problem can be reduced to that now we don't want to maximize, but we want maximize not just with respect to x plus delta over the theta, we want with respect to y, but we want to reduce with respect to some y target class. So we can change it to like this one: maximum delta belongs to set of perturbations, and we can say loss of h theta of x plus delta. With respect to y, we want to maximize, but we can say minus loss of h theta x plus delta and with respect to y target. Okay, so with respect to, we have subtracted this loss with respect to the y target. So this will be reduced. And this can be further converted to a minimization problem. So we can say minimize delta with respect to the set of perturbations, and now we can multiply with the minus, so this will be minus plus. So we can write like this one, that this is minus L of h theta x plus delta y and plus L of h theta x plus delta and then y target. So once you have solved this minimization problem using a neural network, so it means you have created this delta, and then when x plus delta is added to a function or maybe to a model which is h of x plus delta, this will give you a high probability that the class gives the target, not the true class. Okay, so this is all about the in basic introduction about the adversarial machine learning, and we'll do next video on the chapter 2. Thank you.